A routine night at an RAF hangar. A mechanic stirs the wrong paint mix and unknowingly rewrites the rules of war. Hours later, bombers vanish from German radar screens. Was it luck, science, or something stranger? This is the untold story of how one mistake made the Allies invisible. The year was 1942, and the skies over Europe had become the most dangerous place on Earth. Every night, hundreds of Allied bombers lifted off from airfields scattered across England. Their engines thundered through the cold air as they formed into massive formations, bound for occupied France, the Ruhr, or the industrial heart of Germany itself. The men inside those aircraft, many of them barely in their 20s, knew that each mission was a gamble. The Luftwaffe's radar-directed night fighters and the dreaded anti-aircraft batteries, known as flak, stood ready. By the time dawn arrived, dozens of bombers would not return. For the Royal Air Force Bomber Command and the U.S. Army Air Forces, it was clear the balance of technology favored Germany. The British had pioneered radar before the war, but the Germans had mastered countermeasures. By 1941, their radar systems, Freya, Würzburg, and later Liechtenstein, had become the backbone of their air defense network. From deep within the Reich, radar operators could see the dark shapes of bombers crossing the English Channel long before they reached their targets. It was an invisible war of detection and deception, fought in electromagnetic waves. To the men on those bombing missions, radar was a silent enemy. They couldn't see it, couldn't hear it, yet it dictated their fate. And for months, scientists at the Royal Aircraft Establishment in Farnborough and the U.S. Research Station scrambled for an answer. They tried chaff, codenamed window, thin strips of aluminum foil dropped from aircraft to confuse enemy radar. It worked for a time, but it wasn't enough. The Germans adapted quickly. Each new trick from the Allies was met with a countermeasure, and the deadly cat and mouse continued. That's when fate, and a small mistake, changed everything. In the summer of 1943, an RAF maintenance depot in Cambridgeshire, ground crews were preparing a new batch of bombers for the night offensive. The Lancaster, a massive four-engine workhorse of the RAF, had earned its reputation as the backbone of the bombing campaign. Each aircraft was carefully coated in matte black paint, designed to help it blend into the night sky. But one particular batch didn't look right. The finish had an odd sheen, a dull gray shimmer that seemed to reflect the light in strange ways. The story, as later recalled by maintenance workers, began when a supply officer noticed the paint's texture was off. Someone had mixed the wrong components, a different primer, possibly containing iron oxide, into the black camouflage. It wasn't up to spec. The order came down to strip it off and repaint. But time was short, and a handful of aircraft went out with the mistaken coating still on. That night, something strange happened. German night fighter crews, who usually reported radar contacts long before visual contact, began to complain of ghost returns. Several bombers seemed to appear faintly, then vanish from radar screens. Some radar operators dismissed it as equipment error. Others weren't so sure. The truth wouldn't be discovered for weeks, and when it was, it shocked everyone from the hangar floor to the top levels of Allied command. At Farnborough, British scientists were conducting tests on radar cross-section, the measure of how much electromagnetic energy an object reflects back to radar. Their work, often done on scale models suspended from wires and bombarded with radar waves, aimed to understand how to make aircraft less visible. What they didn't yet realize was that one of their accidental experiments had already flown into combat. When engineers analyzed the strange paint sample, they found something unexpected. The mixture contained a high concentration of carbon and iron compounds in microscopic form. This combination, under the right conditions, could absorb portions of the radar signal rather than reflect it. The result was a primitive form of radar-absorbent coating, decades before stealth technology would become a household term. For the Allied scientists, it was a revelation. Up until then, radar had been treated as something to jam, confuse, or overwhelm. Now, for the first time, they had proof that materials themselves could influence radar visibility. The concept that would later drive stealth aircraft like the F-117 and B-2 was born not from deliberate design, but from an error in a wartime paint shop. But in 1943, the discovery remained a closely guarded secret. The war was far from over, and the Allies couldn't afford to reveal that they had stumbled onto something extraordinary. Only a handful of engineers were briefed. Experiments intensified under the guise of surface finish optimization. The RAF began quietly testing different coatings on bomber panels, measuring how radar signals bounced off them under varying conditions. Back at the airfields, the crews noticed something too. Those grayish-black aircraft seemed to fare better on missions. Whether it was coincidence, weather, or something deeper, the statistics began to shift. Fewer of the oddly painted bombers were lost compared to their standard matte black counterparts. Pilots called it luck. Engineers called it data. The Americans soon took notice. At bases across East Anglia, the U.S. Army Air Force's 8th Air Force was flying daylight raids, suffering heavy losses to German radar-guided flak and fighters. If the British had found a material that could help, the Americans wanted in. Cooperation between Allied scientists intensified. At the Massachusetts Institute of Technology's Radiation Laboratory, engineers began exploring radar wave absorption using similar carbon-based coatings. Their goal was not invisibility. That was still a dream. But even a 10% reduction in radar signature could save countless lives. While the Allies moved quietly, the Germans remained unaware. Their scientists, under immense pressure to defend the Reich, were convinced their radar systems were unmatched. The Liechtenstein radar in night fighters like the Bf-110 and Ju-88 was a marvel of engineering, capable of tracking bombers at long range. Yet operators increasingly complained of inconsistent readings. Some targets seemed weaker, harder to lock onto. They assumed Allied jamming or new countermeasures were to blame. Few imagined that paint, of all things, could be the culprit. The irony was bitter. German engineers had pioneered advanced optics, jet propulsion, and V-weapons, but their faith in technological superiority sometimes blinded them to subtler innovations. The Allies, on the other hand, often triumphed through adaptability, through the ability to turn mistakes into miracles. By late 1943, Allied command had noticed measurable improvement in mission survival rates during night bombing campaigns. The Luftwaffe's once deadly radar net began to show cracks. Combined with chaff, electronic jamming, and evolving tactics, the modified coatings made radar detection just unreliable enough to tilt the odds. It was never full invisibility. Far from it. But it was enough to buy precious minutes to delay detection and to get bombers past the most dangerous zones before German fighters could intercept. The war in the air was still brutal. Entire squadrons vanished in flames. Towns across England were littered with the wrecks of returning bombers, riddled with holes, engines smoking, landing on shattered tires. Yet in the midst of this chaos, an accidental discovery had quietly begun to rewrite the rules. In research labs and paint shops, the questions spread like wildfire. Could the Allies go further? Could they design aircraft that radar couldn't see at all? It was a dream that seemed almost science fiction in the 1940s. But in that moment, when a simple paint error turned into a life-saving breakthrough, the first seeds of the stealth revolution were sown. That night in 1943, as Lancaster bombers faded into the clouded sky over the Channel, no one knew that the dull gray shimmer on their wings was history being written by accident. The Germans watched their radar screens flicker and fade, searching for ghosts. And somewhere above the darkness, the bombers flew on, unseen, unstoppable, and forever changed. The discovery at the maintenance depot was more than luck. It was a turning point that revealed how little the Allies truly understood about radar reflection. What began as an accident in a paint shop became a scientific race hidden behind laboratory walls and military secrecy. The first reports from the field, that certain bombers seemed harder to track by radar, reached Farnborough's Air Defense Research and Development Establishment within weeks. The data wasn't dramatic, but it was consistent. Planes with the odd gray finish had a slightly lower radar return. That meant something in the paint was absorbing or scattering radar waves instead of reflecting them straight back. To understand why this mattered, the scientists needed to grasp the fundamentals of radar itself. Radar detection depends on bouncing radio waves off an object and measuring how much energy returns to the receiver. Metal aircraft, with their long fuselages, flat panels, and protruding engines, act like giant mirrors for those waves. A strong reflection gives radar operators a clear target. The only way to escape that invisible spotlight is to either block the radar signal, distort it, or absorb it. Until now, no one had truly succeeded at the last option. The team at Farnborough began experimenting with small aluminum plates coated in different mixtures of paint. They bombarded them with microwave signals, measuring the reflected energy. The mistaken mix quickly stood out. When a radar wave struck its surface, the iron oxide particles dispersed the signal, while the carbon black pigment soaked up part of the energy as heat. Together, they reduced radar reflectivity by a small but meaningful margin, roughly 10 to 15% in early tests. It wasn't invisibility, but it was the first step toward radar absorption. The results were classified immediately. The British government, working under the utmost secrecy, labeled the project under a series of innocuous names like Surface Coating Number 4B. Only a few senior scientists and air officers knew what it really meant. They began collaborating with engineers from the Telecommunications Research Establishment, TRE, the same group that had developed chaff and radar jamming systems. Those men understood that radar wasn't just a detection tool. It was a weapon in its own right. Whoever mastered it could decide who lived or died in the skies over Europe. At the same time, across the Atlantic, the radiation laboratory at MIT, known simply as the Rad Lab, had become the heart of American radar research. When British scientists shared their findings, the Americans responded with enthusiasm. They had been exploring similar concepts in microwave engineering, including wave absorbers used to prevent radar interference inside labs. Those absorbers were made from carbon-based foam materials. The link was obvious. If radar absorbers could control signal reflections in a lab, maybe the same principles could be applied to aircraft. Soon, a joint Anglo-American working group was formed. Their mission: to explore the idea of radar-reducing coatings. The code name was Window Black, a nod to both the chaff operation and the paint's appearance. While these scientists worked in quiet laboratories, war raged on. By late 1943, the Allies were preparing for their most ambitious air campaign yet, to break the industrial backbone of Nazi Germany. The bomber streams had grown enormous, stretching for miles across the night sky. But every flight carried terrible risk. The German radar network had become a masterpiece of coordination, linking early warning Freya systems on the coast with precision-tracking Würzburg units near key cities. Once a formation was detected, night fighters were vectored in to intercept. For air crews, it was a nightmare of searchlights, tracer fire, and engine noise in the darkness. Survival often came down to seconds, the difference between being seen on radar and passing through unnoticed. The Allies needed every advantage they could get. That's why, when early tests suggested the new coatings could delay radar detection even slightly, Bomber Command approved a limited field trial. A squadron of Lancasters was chosen to receive the modified paint, along with other small surface treatments. Each aircraft was carefully measured for reflectivity before and after the application. The results were promising. Detection range was reduced by several hundred yards in controlled conditions. In an era where a minute of delay could mean life or death, those few hundred yards mattered immensely. Behind the scenes, debates erupted among the Allied scientists. Some argued that resources should stay focused on offensive radar and electronic warfare, jammers, decoys, and counter-radar bombs. Others saw the promise of what would later be called stealth. The idea that an aircraft could blend into the electromagnetic background of the sky was revolutionary, even if it was decades ahead of its time. But resources were limited, and war waited for no one. The stealth paint would remain a quiet project, its findings shared only among a select few. The British scientists continued their experiments with different pigments and materials. They found that fine carbon particles worked best when suspended in a resin or oil-based medium. forming a thin but consistent layer that could bond with aircraft aluminum. Too thick, and it added weight and drag. Too thin, and the effect vanished. It was a delicate balance of chemistry, physics, and practicality, the kind of balance wartime engineers constantly juggled. Meanwhile, the Germans pressed forward with their own radar research. Engineers at Telefunken and Siemens worked tirelessly to refine detection systems. The Luftwaffe's night fighters, equipped with the Liechtenstein radar, patrolled the skies with increasing sophistication. Yet, even as their technology advanced, subtle cracks were appearing in their confidence. They noticed anomalies, radar blips that faded too soon, targets that appeared weaker than expected. In their reports, operators mentioned irregular returns and false echoes. German scientists blamed Allied jamming or atmospheric interference, unaware that their enemies had found a way to literally paint their aircraft invisible. By early 1944, the Allies had refined the formula enough to apply it to select bomber squadrons. It wasn't rolled out on a large scale. The production of the special paint was too time-consuming and secrecy too critical. Instead, it was used on specific missions, usually deep penetration night raids, where detection meant disaster. Crews who flew those missions began to sense a difference. Some even described feeling like they were ghosts in the clouds, slipping past radar-guided flak zones with fewer alarms and less interception. The human side of the story was no less powerful. Pilots and gunners who had lost friends on previous missions began to regain a fragile sense of hope. They still faced death every night, but they now carried with them a sense of unseen protection, a shield born not from design, but from error. It was a reminder that innovation in war often comes from unexpected places, from human mistakes that turn into miracles under pressure. As the Allies prepared for the invasion of Europe, radar was about to play its biggest role yet. D-Day depended on deception. The success of Operation Overlord would rely on confusing German radar operators about where and when the attack would come. Chaff, jamming, and radar-reflecting decoys were deployed on a massive scale. But among these elaborate tricks was something much simpler. Bombers and pathfinders coated in radar-dampening paint, flying deep into enemy territory to drop false signals and draw German attention away from Normandy. When the landings began on June 6, 1944, the deception worked. German command centers were slow to respond, their radar screens cluttered with phantom images and fading returns. Though many factors contributed to the confusion, the improved radar coatings helped reduce Allied losses in those critical early hours of the invasion. In the months that followed, the war in the air shifted dramatically. The Luftwaffe, once dominant, struggled to keep up. Allied bombers came by day and night, overwhelming defenses and crippling industry. The Germans tried to counter with newer radar types, even experimenting with infrared detection and anti-chaff systems. But the tide had turned. The Allies' blend of science, ingenuity, and adaptability had begun to erode the technological edge the Reich once boasted. And at the heart of it all was a simple lesson, that in war, the smallest mistakes can spark the greatest breakthroughs. A botched paint mix in an English hangar had led to the birth of a technology that would one day define modern air warfare. The Allied scientists didn't call it stealth. They didn't yet have a name for it. But they understood what they had created, the power to hide in plain sight. By 1944, radar had become the unseen battlefield of World War II. Every raid, every night interception, every flicker on a screen inside a dark bunker was part of a new kind of warfare, a contest fought not with bullets, but with invisible waves. The Allies had begun to master the art of deception in this electromagnetic domain, and their quiet advantage, born from that accidental paint mix, was shaping a new phase of air superiority. The skies over Europe had changed. What began as desperate survival had evolved into calculated strategy. Allied command understood that radar wasn't just an enemy's eye. It was their weakness, too. If you could blind the radar, or even make it hesitate, you could control the tempo of the war. Inside the Royal Air Force's Bomber Command, a network of scientists, engineers, and intelligence officers worked hand in hand, feeding discoveries from laboratories directly into operations. Their mission was clear: make the bombers untouchable. At the center of this effort was Farnborough, where physicists had turned the paint mistake into a scientific curiosity with military potential. The research had evolved from simple coating tests to more complex studies of electromagnetic wave absorption. They began experimenting with multi-layer coatings, thin films that alternated between carbon-based materials and metallic oxides, to disrupt radar reflections even further. Each layer interacted differently with radar wavelengths, scattering some signals, absorbing others, and creating interference patterns that confused enemy receivers. By now, the Allied radar labs in Britain and the United States were effectively conducting stealth research decades before the concept even had a name. At the Massachusetts Institute of Technology's Rad Lab, teams of young physicists, many of them future Nobel laureates, ran tests using scaled models of aircraft coated with experimental finishes. They recorded how radar signals bounced off curved surfaces, how angles and materials influenced detection. The data was crude by modern standards, but it laid the foundation for the mathematical models that would later define stealth design. One engineer, working on B-24 Liberator components, noticed something remarkable. By combining certain carbon mixtures with a resin binder, the radar reflection could be reduced by nearly 20% in some frequencies. The coating was fragile and prone to peeling under wind and rain, but the implications were staggering. Even a marginal reduction in radar visibility made enemy tracking less accurate, which meant fewer successful interceptions. The Germans, meanwhile, were beginning to notice something was off. Night fighter squadrons flying out of bases in France and Germany were reporting erratic results. Some radar contacts disappeared mid-approach. Others seemed weaker or distorted. Crews grew frustrated as bomber formations slipped through despite the intricate radar net. The once reliable Liechtenstein radar was now prone to confusion, not just because of chaff, but because of something subtler. German intelligence officers began collecting radar fragments from downed bombers, scraping paint from their fuselages for analysis. At Peenemünde, a center for advanced weapons research, scientists examined the strange coatings. They confirmed the presence of high-carbon compounds and unusual primers. The conclusion was puzzling. These weren't standard camouflage materials. Yet even as they suspected deliberate Allied innovation, they underestimated its significance. German leadership was consumed with larger projects, V-weapons, jet aircraft, and late-war wonder weapons that promised to reverse their fortunes. The idea that a paint could bend the course of aerial warfare seemed too trivial to matter. That arrogance cost them dearly. As the Allies gained confidence, they refined the coatings for practical use. The British focused on maintaining the material's radar-absorbing properties without compromising weight or durability. The Americans went further, exploring industrial applications. Factories in the UK and the US were quietly instructed to produce limited quantities of the special paint, shipped under vague descriptions like anti-reflective coating compound. Only select aircraft in high-risk missions received it: pathfinders, reconnaissance planes, and long-range bombers operating deep in enemy territory. Inside these aircraft, air crews were unaware of the full science behind their missions, but they knew something had changed. The most experienced pilots spoke of radar searchlights taking longer to lock on, of German fighters arriving late or missing entire formations. They chalked it up to skill or luck, but intelligence officers collecting after-action reports could see the difference in numbers. Loss rates had dropped slightly, sometimes by just a few percent, but those percentages meant hundreds of men returning home alive. Meanwhile, Allied scientists pushed deeper into radar theory. They discovered that certain frequencies were more easily absorbed by the coatings, depending on weather, humidity, and altitude. The British H-2S radar system, used for navigation and bombing, helped gather return data from enemy radar emissions during missions. It was an early form of radar espionage, where bombers acted as flying laboratories, collecting signal behavior while dodging flak. By the spring of 1944, radar research had expanded beyond materials. Engineers realized that the shape of the aircraft itself, played a role. Sharp edges and perpendicular surfaces reflected radar energy more strongly, while curved or sloped surfaces scattered it. Although it was impossible to redesign the massive bombers mid-war, subtle adjustments were made: smoother nose cones, rounded fairings over gun turrets, and thinner antenna mounts, all to reduce the radar signature. The line between engineering and survival blurred completely. At the same time, the war's emotional toll deepened. In briefing rooms across England, aircrews studied radar maps, tracing the invisible lines that could lead them to death. Veterans remembered the first missions before these advances, when radar-guided flak was so precise that bombers flew through what looked like a wall of fire. Now, even with the improvements, every flight remained a deadly gamble. But hope had replaced despair. For the first time, it felt like the science of war was finally catching up to the courage of those who fought it. As the Allies advanced after D-Day, radar became both weapon and shield. The same principles that made bombers harder to detect were now used to protect naval convoys crossing the Channel. Engineers experimented with radar-absorbent coatings for small vessels and submarine periscopes, testing ways to reduce reflections from German coastal radar. Even tanks were briefly tested with dull, carbon-coated finishes, though the practical benefits were limited on land. Still, it showed that the idea had taken hold, that invisibility wasn't fantasy, it was a future worth pursuing. By late 1944, German scientists finally realized what they were facing. Reports circulated describing Allied bombers with radar-dampening coatings. But by then, it was too late. Their radar operators were overwhelmed by jamming and deception, their supply lines crumbling, their airfields bombed daily. They no longer had the time or resources to replicate or counter the technology. The once feared Luftwaffe had been reduced to a shadow of its former self, its best pilots gone, its radar advantage neutralized. In Washington and London, senior officials quietly reviewed post-mission data and research summaries. They understood they had stumbled onto something revolutionary, not just for this war, but for wars to come. A few visionary scientists proposed formal programs to explore radar-absorbing materials in peacetime. One British physicist, writing in a classified report, suggested that the deliberate control of radar reflection may one day permit aircraft to evade detection entirely. His idea sounded like science fiction, but the seed had been planted. The war's end was near, yet the Allies weren't done experimenting. Late in 1944 and early 1945, small-scale tests were conducted on prototype jet aircraft, including the British Meteor and captured German Me-262s. These trials aimed to measure radar reflection at higher speeds, using coatings based on the original paint discovery. The results were encouraging. The faster the aircraft flew, the harder it became to track accurately. It was a glimpse of the jet age to come, one where speed and stealth would rule the skies. Still, the full significance of the accidental paint mix was known to only a few. To the public, victory would be credited to courage, strategy, and firepower, and rightly so. But inside locked archives, folders marked confidential, radar countermeasures told another story. One of scientists who turned error into advantage, and engineers who found a way to make steel ghosts glide unseen through the night. For the men who flew those missions, it was never about the science. It was about getting home. Many didn't know that the dull, grayish-black coating on their aircraft skin was part of what kept them alive. They never knew that their survival rested on a laboratory mistake. But history would remember it, not as an accident, but as the moment the Allies began to win the invisible war. The skies over Europe, once bright with tracer fire and explosions, were slowly turning in the Allies' favor. Beneath that night-black paint lay not just a layer of chemistry, but the beginning of an idea that would define military aviation for the next century: the dream of invisibility. When the war finally began to tilt in the Allies' favor, the secret of the invisible paint was quietly buried under piles of classified reports and coded memos. The technology had done its job. It had saved lives, confused German radar, and proven that the sky could be shaped not just by metal and power, but by science. Yet, like so many wartime breakthroughs, it vanished into silence once victory seemed assured. By the spring of 1945, Allied dominance in the air was absolute. The German radar network, once a marvel of precision, lay in ruins. Bombing raids no longer required the same desperate tricks that had defined the earlier years. But in laboratories across Britain and the United States, the scientists who had guided the paint experiment knew what they had stumbled onto was far greater than a short-term fix. It was a glimpse into the future, a new frontier of warfare defined not by visibility, but by control over the unseen. At Farnborough, the researchers filed their findings under a series of restricted reports. One of them, labeled Absorptive Coatings for Aircraft Application, 1944, summarized everything they had learned. That radar reflection could be influenced by surface materials, that iron and carbon mixtures could absorb microwave energy, and that with refinement, radar invisibility might one day become achievable. It was a visionary conclusion, decades ahead of its time. The documents were sealed under the Official Secrets Act and stored away, forgotten by everyone except a few men who understood what they represented. In the United States, a similar story unfolded. The scientists at MIT's Radiation Laboratory finished their wartime contracts and returned to universities and private industries. Many of them would later pioneer the very fields that would make stealth possible: microwave physics, materials science, and electromagnetic theory. They had seen the birth of radar during the war, and now they carried with them the faint memory of its first challenger, radar absorption. The accidental paint that had started it all disappeared into history's shadows. The manufacturing formula, improvised under wartime stress, was never standardized. Once the emergency production runs ended, the remaining batches were used up or discarded. By the time peace returned, no one saw the need to preserve it. The world was exhausted, and attention shifted from survival to reconstruction. But the idea didn't die. In 1946, both British and American defense committees began drafting secret reports on low radar reflectivity technologies. They cited wartime experiments with coatings, angles, and composite materials as the starting point. The concept was now official. Radar invisibility wasn't a myth, it was an engineering challenge. Over the next decade, that challenge would quietly evolve, buried within classified research programs. The Cold War would awaken the old dream. As the United States and the Soviet Union raced to dominate the skies, radar once again became the eye of power, now sharper, stronger, and capable of tracking jets at hundreds of miles. The memory of those World War II experiments returned to relevance. In the 1950s, American engineers began developing radar-absorbing materials for the U-2 spy plane and later for the A-12 and State Route 71 Blackbird. Their principle was the same as the mistaken wartime coding: absorb, scatter, confuse. What began in an English paint shop had become the foundation of modern stealth. Back in Britain, some of the wartime researchers revisited their notes in the early 1950s, astonished to see how far the science had come. They had never imagined that a paint meant to hide bombers in the night would evolve into a discipline that shaped global strategy. The irony was that the original discovery, the accidental mix that made radar fade, was still technically classified, known only to a handful of historians and scientists. For the men who had flown under that gray-black paint, the war's memory was personal, not scientific. They remembered the cold, the fear, the endless hum of engines over the channel. They remembered friends who never returned. What they didn't know was that the strange, dull coating on their aircraft had changed the way war would be fought forever. That mistake had quietly rewritten the playbook for generations to come. As decades passed, the story faded from official histories. It wasn't until later that declassified research hinted at its existence. A wartime coating that reduced radar reflection, discovered by chance. Historians found fragments, test notes, radar data, field reports describing anomalies in enemy detection. There was no headline, no hero, no single inventor to credit. Just a chain of ordinary people. A factory worker mixing paint under pressure. A mechanic who noticed the strange sheen, and scientists curious enough to measure what others ignored. That's how history often turns, by accident, by human curiosity, by the quiet persistence of those who refuse to dismiss the unexpected. The lesson of that wartime mistake was never really about radar or chemistry. It was about innovation itself, about how the smallest errors can shift the balance of power when the world is watching. The Allied advantage in World War II was not only its industry or manpower, but its ability to adapt, to find meaning in mishaps, and to turn chaos into opportunity. The dull, carbon black paint that once made bombers vanish in a night would one day inspire aircraft invisible to all but the most advanced sensors. From the B-2 Spirit to the F-35, the legacy of that accidental discovery lives on in every shadow that slips unseen through the modern sky. It all began with a mistake, a wrong mix on a rainy day in an RAF hangar. No one could have known that a few misplaced ingredients would mark the birth of a revolution. But history remembers not the error, only what it became. The first step toward invisibility.